Hello again, everybody. In the last few lectures, we talked about how one could go about computing the band structure of periodic solids using a couple of very powerful but also somewhat elementary developments. One was the nearly free electron method, and the other one was the tight binding method. It turns out that both of those methods are really the methods of choice even today for the computation of the band structures of solids, as well as computing the total energy as well as other properties of solids, but also systems such as molecules, atoms, nanostructures, and so forth. In fact, interestingly, already by the 1930s, the scientific framework was already available, was put in place for calculating the electronic structure of atoms, molecules, and periodic solids. That's quite incredible because that's barely 10 years after the Schrodinger's equation was actually written down. And there is our Schrodinger's equation. We are of course assuming that this is for a periodic solid, which is why the indices k are stuck into the wave function and the energy. Okay, so this is the equation that we have been attempting to solve in the last few lectures. And let me just write down how we went about handling the nearly free electron and the tight binding situations. So within the nearly free electron approximation, or NFE, we write down the wave function as a Fourier series. Right? The wave function, of course, needs to satisfy Bloch's theorem because our Hamiltonian and the potential display periodicity. And so the wave function psi of r has to be a product of the phase factor e to the ik dot r times a periodic function uk of r. Now, because uk of r is a periodic function, it can be written as a Fourier series, and which is why we have this given expression for our wave function. The Fourier series is also called as a plane wave expansion. So although I'm calling this as the approach that we adopted within the nearly free electron approach, I have to state here very clearly that this expansion of the wave function, as long as this series is infinite, is in principle exact, right? It's just that we need to truncate this infinite series at some point to make calculations practical, and if you truncate it to some kind of an extreme situation, we get the nearly free electron model. But if we extend the series further on, we can get results with increasing levels of accuracy. Okay, so that's what we do when we attempt to solve this problem using the plane wave expansion. Now let's see what expression we got when we tried to use the tight binding approach. So there it is. This is the tight binding, or the TB method. Within this method, the wave function is written as a expansion over local atomic orbitals. Right? So it looks a little bit cumbersome. Nu is really an index that keeps track of the local orbitals such as the 1s, 2s, 2p, 3s, and so forth. And the term within the curly brackets is constructed so that it automatically satisfies Bloch's theorem, although it's not entirely obvious if you just look at that in this manner. But we proved that the term within this curly brackets satisfies Bloch's theorem in the previous lecture on tight binding method. And phi, the small phi of nu that we have over here is our local atomic orbital, right? It's a local function. It's an atomic orbital, such as the 1s, 2s, 2p, and so forth orbitals. So we have once again an expansion over atomic orbitals in this case. So the plane wave expansion involves the expanding the periodic part of the wave function in a series, Fourier series. The tight binding approximation involves expanding the wave function as a linear combination of atomic orbitals, a linear combination chosen such that it satisfies Bloch's theorem. In both cases, we have expansions. Okay, so now let us bear this in mind, and let's write down the Hamiltonian itself, which should be very familiar to us by now. So we have our Hamiltonian, which has a kinetic energy operator and a potential energy V of r. As long as V of r is specified, which is of course specified once we know the system we are trying to address. Um, so once V of r is specified, and once we know the wave function form that we are going to choose, which is either this or that, we stick it into our Schrodinger's equation, and the solution of the Schrodinger's equation would give us the energy values as well as these coefficients, right? This set of numbers over here, or this set of numbers over there. So knowing those, either this set of numbers or that set of numbers is equivalent to knowing the wave function itself. So solving the solving the Schrodinger's equation with this as the Hamiltonian, with a suitable choice of the potential, is going to lead us to our answers, which are the energies and the wave functions in terms of the coefficients u or c. Unfortunately, life is not that easy. There are two hurdles to the solution. In fact, it's because of these hurdles that in the last couple of lectures we made significant and extreme approximations to get to some qualitative picture of what the final answer should look like. Right? Properly solving this problem is not trivial. There are two general hurdles to this problem, and let's very briefly list those two hurdles. So the first hurdle was of a practical nature, right? This is something I already alluded to. Regardless of whether you use the plane wave expansion or the local orbital expansion, you have in principle infinite number of terms in that series, and we truncate that series. If we do want to achieve a certain level of accuracy, a satisfactory level of accuracy in our final results, it turns out that you need to have series expansions that are rather large. This became too cumbersome to handle, in the 1930s, 40s, 50s, and so forth, because modern type computers did not exist at that time. So it was rather laborious to solve these equations. That was a practical issue. There was a technical issue which we have kind of swept under the rug, in the last several lectures. The technical issue relates to our choice of V of r. We have always been claiming that V of r is really a periodic potential due to the nuclei, right? So you have a periodic arrangement of nuclei which will lead to piecewise addition of the Coulomb potentials due to each nuclei, which will lead to a periodic potential. Well, that is certainly true, that the nuclear potential is certainly one part of V of r. But V of r is a lot more than that. V of r also includes the electron-electron interactions. You see, in the last couple of lectures, we have implicitly assumed that we have a single electron inhabiting a periodic potential due to the nuclei. But in reality, you have a large number of electrons. So these electrons are interacting with each other. So just like each electron is being attracted by the nuclear potential, they're also being repelled by the other electrons. And there are also exotic quantum mechanical interactions that our electrons encounter. And these are called exchange correlation interactions. So our V of r, the potential V of r that goes into the Hamiltonian, has nuclear electron interactions, which we have addressed so far, but they also need to include the electron-electron interactions, which are very difficult to properly, adequately treat. Today, fortunately, both of these issues are handled quite well, quite satisfactorily. The first issue, the practical issue relating to the cumbersome nature of the series and the solutions that involve rather long series expansions, can be very beautifully handled by modern powerful computers. The second issue, which deals with the electron-electron interactions, is also handled quite well in modern times due to the work of many people, but most notably John Slater, who developed this method called the X-alpha method, which is going to be beyond the scope of this course. Um, so John Slater was one person, and the second person whose name comes up within this context is Walter Kohn, who developed this method called the density functional theory, which today is perhaps the most popular and most widespread quantum mechanical theory for materials modeling, materials computations. Again, that theory is also beyond the scope of this course. In fact, that's a different course altogether. The point I'm trying to make is that both of these issues today are adequately solved. Of course, there is always room for improvement. Even today, we do make several approximations which lead us to some other set of issues, but we are in much better shape today than we were 80 years ago. Well, but the point is that even 80 years ago, in the 1930s, people were actually able to solve the band structure problem for solids. In fact, the biggest contribution, the monumental contribution that came in that time was the one due to Wigner and Seitz. And that's exactly what we are going to explore right now. We are going to ask the question as to how Wigner and Seitz were able to handle this problem for a true solid at a time when computers did not exist and theories to properly handle electron-electron interactions did not exist. So Eugene Wigner and Frederick Seitz got together in the early 1930s, and they wanted to solve the band structure problem, solve the Schrodinger's equation for solid sodium. There were two reasons they chose sodium. One of them is that sodium has a single 3s valence electron. So if you were to ignore the core electrons, you have just a single valence electron that you need to treat, and in that sense sodium atom rivals the hydrogen atom in simplicity. So that was one of the reasons. The second reason is because the sodium solid occurs in a body-centered cubic, the BCC crystal structure. If you consider the BCC lattice, you will realize that the unit cell, the Wigner Seitz primitive cell of this particular lattice is more or less spherical. In fact, it was to handle the sodium solid problem using the Schrodinger's equation that Wigner and Seitz came up with this whole idea of the Wigner Seitz cell. In fact, until that point, unit cells would be defined in the traditional, conventional way, and it was Wigner and Seitz, in order to handle this particular problem, that they came up with this whole idea of defining unit cells in a different manner, which led to unit cells that were more or less spherical. In fact, this is how our Wigner Seitz cell looks for a BCC lattice. Right? So remember that in the BCC case, we have lattice points at the corners of a cubic lattice, and you have a lattice point at the center of each of the cubes as well. Right? So if you follow through the Wigner Seitz construction to create a primitive unit cell around a reference lattice point, you would get this more or less spherical shaped polyhedron as the primitive unit cell. Okay, so this is the reason Wigner and Seitz chose sodium. It has one valence electron, and so if you ignore the core electrons, you have just one electron to deal with, very similar to hydrogen, the hydrogen atom. But unlike the hydrogen atom, your sodium atom is part of an infinite solid. But The sodium atom is part of a periodic solid, and the periodic unit cell that is appropriate here is the Wigner Seitz cell, which looks more or less spherical. So the natural question is, okay, so what? How is all this going to help us out? How did all this help Wigner and Seitz out? So before we attempt to answer this question, let us attempt to find out how the electronic structure of our system, of our sodium solid, is going to look like as a function of the internuclear distance. In other words, as a function of the lattice parameter, right? If the lattice parameter of our sodium solid goes to infinity, we essentially have a single sodium atom, an isolated sodium atom, right? And as the lattice parameter decreases and approaches its equilibrium value, our sodium atom, the electron wave function of our sodium atom is going to interact with all the neighboring ones, and so we expect to see some changes in the band structure, in the electronic structure, just as we have encountered in the past, right? So let us now make a schematic plot of how we expect the electronic structure to look as a function of the internuclear separation or the lattice parameter. Okay, so here is our electronic structure as a function of the internuclear or the interatomic spacing R. R naught is the equilibrium value of our interatomic or internuclear spacing. And what we are really saying is that when R is very, very large, we recover our atomic result in the sense that our energy levels would simply be the atomic 1s, 2s, 2p, 3s, and so forth energy levels, discrete levels. As we make our R smaller and smaller, our wave functions, our atomic orbitals will start interacting, overlapping with each other. We start forming these linear combination of atomic orbitals, as we have seen many times before, and our energy levels will also start broadening. But this broadening will really occur only at very high energy levels that are high in energy. So the core levels, the 1s level, will be unaffected by the interatomic spacing because they are so low in energy, and they are the wave functions are also so close to the atoms themselves, so they don't really see the effect of the neighboring atoms. So the core levels, which are the 1s, 2s, 2p, do not get affected by the fact that our atom is really part of a solid. It's only the valence levels, higher energy levels, that see the full effect. In fact, chemical bonding is essentially because of the valence electrons. This is why we make a distinction between core and valence electrons in the first place. So it's only the valence levels that see the maximum effect, and as a result, you see this what was originally a discrete 3s level, our valence level in sodium. As you decrease the internuclear spacing, the 3s level starts interacting with the neighboring ones, and you get various linear combination of atomic orbitals and a spectrum of energy levels that become occupied. So that's what is schematically depicted over here. So there is a broadening. All of these energy levels now are allowed in our solid sodium, and these energy levels are of course connected to wave functions which are various linear combinations of our 3s level. So at this spacing, there is a spectrum of energy levels that are derived from the 3s atomic orbital that become allowed. Whereas, of course, 2s, 2p, and 1s level, which is way down below, they still remain discrete. And of course, this is just a schematic over here. It's not like the 2s and 2p will be on top of each other throughout this entire spectrum of interatomic spacings we are considering over here. But the point is that these core levels are relatively unaffected. So they can be ignored. This was the rationale. Right? Of course, if we want to be a little more precise, we need to draw the same kind of picture that we drew for the 3s level for the 3p as well, because it's 3p is going to be somewhat close in energy to the 3s level, And so if let us just put that also in this plot just for completeness. So there is a 3p level which is also undergoing this kind of a not exactly splitting but broadening, right? So it's a range of energy levels that become allowed now, and they are all 3p derived energy levels. Of course, calling some level over here as a 3s or 3p derived is not entirely correct, because there is mixing between the 3s and 3p. This is what we call as hybridization. So the spectrum of energy levels in this range are really a mixture of 3s and 3p is what we should say. But for now, we are going to consider just the 3s level, which is what Wigner and Seitz did. What they actually did was really map out just this bottom part of this curve. Right? They ignored the core levels, they ignored 3p, and they focused on 3s, and they attempted, they tried to just map out just the bottom part of this curve. That's it. From that, they were able to derive a lot of important conclusions. Okay, let's now qualitatively try to understand why we expect this sort of a behavior for this bottom part of the band. Bear in mind that this is a band, right? This whole thing is a spectrum of allowed energies, essentially that is our valence band. So when R is very, very large, all of the atoms, all of the sodium atoms will display a 3s energy level, which is exactly equal to that. Meaning, if you have n atoms in your system, where n is of course a very large number, you will have n degenerate 3s levels, meaning all the n different 3s levels, one of which due to each atom, is going to have exactly the same energy, meaning that they are degenerate. So when R is very large, the 3s levels are all, the n different 3s levels are degenerate. As R shrinks, as you bring R down, you are going to create these combinations of atomic orbitals, and each one will have its energy. And of course, if you recall, the bottommost energy is of course the one due to the bonding combination of all of the atomic orbitals through and through. And likewise, the topmost part of the band allowed set of energy levels is going to be dominated by anti-bonding combination of the atomic orbitals through and through. In fact, the topmost one would be entirely anti-bonding between any two adjacent atoms. You may recall that we use the K to label all of these different combinations, and the bottommost one corresponding to the bonding combination of atomic orbitals is indexed by K equals 0. And this is something that we can actually very nicely see by considering the tight binding scheme for the wave function, where if you just set K equals 0, you will get just a simple addition of all of the atomic orbitals of the system. You may also be wondering why the bottom part of our 3s level is actually going down first and then going up. That is somewhat easy to understand. Initially, as you keep decreasing your R, the favorable nature of the bonding combination of the wave functions is going to drop the energy down. But as you squeeze your R to rather small values, the favorable interaction is going to get more than compensated by the unfavorable nature of squeezing electrons in a very small space. And because of that repulsion that electrons would face, the bottom part of the band would actually tip over and go up. Now, you may also be wondering why our equilibrium spacing, interatomic or internuclear spacing, or the lattice parameter, is not coinciding with the bottommost part of our the bottom of our 3s band. The reason for that is this R naught is determined by the total energy of our system, and what is plotted over here is just the electronic part of that total energy, right? So for any given value of R, you have let's say this is a particular value of R we are looking at. We have a range of energies that are energy levels that are derived from the 3s atomic orbital that are allowed. So you have a range of energies over here, right? we need to occupy these energy levels with electrons until we run out of electrons, right? So we start from the bottom, and then until we run out of electrons, we occupy these energy levels, and at some point we will run out of electrons. Let's say we run out of electrons somewhere over there. So all of these energy levels are occupied with electrons. The total electronic energy is going to be some kind of a sum over these energy levels. That's what is going to provide us with the electronic part of the energy, of the total energy. To that electronic part, we of course need to add the nuclear repulsion part, and this is something we had considered when we discussed the hydrogen molecular ion, the H2 plus molecular ion. So we computed the electronic part of the energy, total energy, and to that we added the nuclear part, and that gave us the total energy of the system, of the H2 plus molecular ion system. We plotted that total energy as a function of the internuclear distance, and we saw that there is a minimum, and that is actually the minimum that corresponds to the equilibrium interatomic spacing of that system. Likewise, here too, the equilibrium interatomic or the internuclear spacing is going to be determined by the total energy, and what you're seeing here is just the electronic energy. Having said that, I should also note that the R naught typically occurs indeed close to the minimum of this picture over here. But in order to keep things general, I intentionally put the R naught, not exactly at the minimum. Okay, so how did Wigner and Seitz go about determining this part of the 3s band, the bottommost part of the 3s band? How did they do that? In order to understand that, let's make an observation. If you consider the hydrogen atom, the isolated hydrogen atom, we know that the boundary condition for the wave function for that particular problem is that the wave function has to go to 0 as you go to infinity, as you go far away from the nucleus, right? In fact, for the correct value of the energy, if you now solve for the wave function, you will get a wave function with the correct boundary condition. The wave function will go to 0 as you go far away from the nucleus. On the other hand, if you go back to your Schrodinger's equation and stick in a wrong value for the energy, and then attempt to solve for the wave function for that wrong value of the energy, you will get a solution for the wave function for sure, but that solution will not have the correct boundary condition. The wave function for the wrong value of the energy will be something which will not go to 0 as you go to infinity. Wigner and Seitz knew that, and they wanted to exploit this observation. Let us actually use this idea and attempt to draw what we expect for the wave function of the 3s level when we use the correct energy for the 3s level versus the wrong energy. So there is the radial equation, Schrodinger's equation, that we wish to solve for our hydrogen atom or for our sodium atom, and it turns out that we can do that by sticking in various values of E and solving for the wave function psi numerically that would satisfy this particular equation. So if we chose the correct value of the 3s energy level for this E, here is what we would get. So there it is, our 3s wave function. Note that there are a couple of nodes because it is the 3s function. If it was the 1s wave function, there would be a 0 node. If it is the 2s wave function, there would be 1 node, and this is the 3s wave function, it has 2 nodes. But the important point to note is that as you go to large values of R, our wave function goes to 0 asymptotically. That's the correct behavior for an isolated atom. And when we stick in the correct value of the 3s level. Now let's see what happens if we chose the wrong value for this E. If we chose some other value for E, and if we attempt to solve for the Schrodinger's equation, what would happen? So here is an example scenario, right? So when the energy that we use in our Schrodinger's equation is not equal to 3s, in general we could get a solution of this type, right? We are assuming here, of course, that the energy, the E that we have chosen is not equal to 3s but close to it, and for that reason the form of this wave function is roughly the same as over here for the most part, except that as you go to large values of r, it kind of diverges. Let us make another important observation. For this case over here, you see there are two values of r for which the wave function is not 0, but the slope of the wave function is 0. So as r goes to infinity, of course the wave function diverges, but there are two important points, values of r, for which the slope of the wave function is equal to 0. Now why is all this important? In order to see that, let us go back to this picture over here. Bear in mind that the goal of Wigner and Seitz was to map out this line. Right? That's really what they wanted to do. And they of course knew that the wave function that corresponds to any point on this bottom part of the band is the bonding combination of all the atomic orbitals, meaning it's just a simple sum of the atomic orbitals of all of the atoms. And when you perform such a very simple sum, the slope of the wave function at the bond center has to be equal to 0. So here is an example of such a situation, just a bonding combination of all the atomic orbitals from the various atoms just added up, right? That would be the sort of wave function that you can expect at for the energy levels at the bottommost part of our band. And when you have a situation like this, when you simply add up the wave functions, atomic orbitals due to all of the atoms of the system, you will see that at the bond center, the slope of the wave function has to be equal to 0. In the case of the sodium solid, of course, this means that the slope of the wave function will have to be 0 at the Wigner Seitz cell boundary. So what Wigner and Seitz did was to essentially replace this truncated octahedron, right? You got a polyhedron over here. It's really an octahedron that has been truncated. In any case, so what Wigner and Seitz did was simply replace. They found the volume of this polyhedron, which is quite trivial to compute. They replaced this volume with a sphere of equal volume, and all they needed to do was to identify or determine 3s-like wave functions which would have a slope 0 at the radius of this Wigner Seitz sphere. Essentially, they just restated the boundary condition for this spherical problem, and they went about determining the energy values for which they would get wave functions with slope equals 0 at the boundary of the sphere. This now became a completely tractable problem. Now let's pay attention to this figure, the bottom part of our 3s band, of course. For any choice of E, right? You stick in this choice of E in our radial Schrodinger's equation, and if this is a general value of E, then you would get 2 radii at which the wave function would have a 0 slope. We already saw this earlier, and here it is. You see, for a value of E that is not equal to 3s, you would get this kind of a wave function, and there are two radii at which the slopes of the wave function are equal to 0. So let's call them R1 and R2, right? For a general value of E, there would be two values, R1 and R2 of the radii, of the radius, at which the slopes of the wave function would be equal to 0. Now let us go back to our band structure picture over here, and let me now make the note that for a general value of E, you actually have two points over here that correspond to that same value of E, and in fact those 2 points are the two radii R1 and R2 that we just marked in the wave function plot. So all Wigner and Seitz did now was to choose different values of energies, somewhat close to the 3s level, right? If they use the value of energy equal to exactly equal to the 3s level, they would get the 3s solution, which they already knew. Now what they did was change the value of energy slightly, right? Systematically they changed the value of energy, and they did it for a few different values of energy, and for each choice of energy they got two values of the radius for which the slopes would be 0, and then and that gave them 2 points, right? So for each value of energy that they chose gave them 2 points in this plot, and they chose like 5 or 6 different values of energy, and they got 5 or 6 different pairs of points in this plot, and that helped them map out this bottom part of the conduction band. Okay, let's just very quickly recap all of these nice ideas very briefly. So the first step was that Wigner and Seitz replaced their Wigner Seitz cell with a sphere of the same volume, and in addition they required that the 3s wave function have 0 slope at the boundary of that sphere, right? So this step actually allowed them to solve a spherical problem, right? So that was a huge simplification. So that was the first step. And the second step was to choose various values of E, and for those specific values of E, they solved the radial Schrodinger's equation to determine the values of R1 and R2, the two radial points for which the wave function would have 0 slope. And once they determined R1 and R2, Wigner and Seitz were able to map out the bottom of the 3s band. And then in the final step, they were able to use the free electron theory to determine the occupations of the band. This is something we had encountered before, how to occupy bands using, let's say, the Fermi-Dirac statistics. So they used the free electron theory to determine the occupation of the various energy levels within the 3s derived band, and from there on they had to jump a couple of hoops, and then eventually they were able to get the total energy of the system. So once you get the total energy of the system as a function of the internuclear separation or the lattice constant, you can actually compute a number of other nice properties, such as the equilibrium lattice parameter, the cohesive energy, the bulk modulus, and so forth. In fact, Wigner and Seitz determined all of these 3 properties, which matched up really well with experiments. Let's make a quick plot and a brief table to capture these ideas. So here is a plot of the total energy as a function of the internuclear separation R. The total energy goes through a minimum, and the minimum occurs at a value R naught, which can be related to the lattice parameter. So you can actually determine the value of the lattice parameter using this entire scheme. In addition, this energy difference over here is what we call as the cohesive energy. That is the energy required to take the solid and convert it to a bunch of isolated atoms, right? So that's the cohesive energy. So using this scheme, we can compute the cohesive energy. In addition, the curvature at the minimum is related to the bulk modulus. So by evaluating the curvature, you can actually determine the bulk modulus itself. As I mentioned, Wigner and Seitz determined all of these 3 properties, and their determinations are listed over here for the lattice parameter, the cohesive energy in kilocalories per mole, and the bulk modulus B. Right? So these are the 3 numbers that Wigner and Seitz report in the early 30s, and here are the corresponding experimental numbers, and you can see that the agreement is quite spectacular. given the approximations that Wigner and Seitz made, but more importantly, given that no fitting parameter was used in this determination. So this contribution by Wigner and Seitz was indeed monumental, because it showed for the very first time that fundamental atomic level properties such as the lattice parameter, cohesive energy, bulk modulus, and there are many more that can actually be computed by solving Schrodinger's equation for an appropriate model of the real system, and by using absolutely no fitting parameters in the entire process. So this is quite an amazing achievement, and of course Wigner and Seitz made a number of approximations because they had to um, deal with the lack of modern computers at that time. Today we can do a much better job, and we can do the same sort of thing for pretty much any solid, and we can get not just the band structure of the solid in the entire Bravon zone, but we can also compute various properties of this type. This concludes our lecture for today. Thank you.